Hi everyone, welcome back to our channel. Today we are going to understand about the steady state behavior of an pure capacitor. Okay, so steady state, what is meant by steady state behavior and how it behaves when an sinusoidal supply is given. So here we are going to take an sinusoidal supply and we are going to apply it to an capacitor of C farads. Okay, now what happens to it? So the input what we are going to apply is small v equal to v m sine omega t. Then it is going to develop a current I. Okay, now how to get this current? So when you give the current to the capacitor, what will happen is the current flows to the capacitor and it will gets charged. Okay, so this I am going to draw. X-axis is t and y-axis is current. So the inductor gets charged, slowly it gets charged and it reaches an final state. Okay, so these are the two states of the capacitor. The first state you are going to call it as transient state and the next state you are going to call it as steady state. Why? Because transients are available for lesser time and only 4 times. So if you take tau is equal to 0.1, it is available only for 4 milliseconds, and after 4 milliseconds whatever it is there, the capacitor has been fully charged. Okay, this is what the behavior of the capacitor in terms of a transient time as well as steady state time. So now let's try to derive the relation for it. So we know the formula for current I is equal to dq divided by dt. Okay, and we can write down the formula for q is equal to cv. There is nothing but d by dt of q can be written as cv and v can be written as like this. So d by dt of c into the voltage given is v m sine omega t. So from here c is a common term, vm is a common term. So d by dt of sine is nothing but, already we know that from the basics, differentiation of sine t is equal to cos t. So from here c into vm d by dt of sine theta is cos theta and the differentiation of omega t is into omega. So therefore I can write down this as Vm divided by 1 by omega c into cos of omega t. Okay, and already we know that cos omega t can be written as a sine of pi by 2 plus omega t. So why? Because sine 90 is how much? Cos, and whenever it is 90 plus theta will be in second quadrant. In second quadrants all silver, it starts with sine, automatically are going to get positive. Okay, so then we are in second quadrant. So this is nothing but sine pi by 2 plus omega t can be written as cos omega t. So this I'm going to call it as Vm divided by, and this xc I'm going to call it as 1 by omega c. So here I'm going to write down 1 by xc, 1 by omega c as xc ohms, and cos omega t I can write down it as sine omega t plus pi by 2. Okay, so from here this is I of t. So I of t v maximum by r, I can write down it as I maximum, I of t equal to I maximum sine of omega t plus pi by 2. So when you see here, so this I want to write down the RMS. Okay, so this is instantaneous quantity which is varying. So I want to write down the current in polar form. So when you write, need to write down in polar form, this is the maximum, but here we are going to get the RMS quantity. That's why Im by root 2 into the angle made. The angle made here is plus 90 degrees. So this is what the formula we are going to get. And now we need to understand about what is meant by XC. Okay, so XC is nothing but capacitive reactance. So here xc ohms is equal to 1 by omega c, where c is called capacitance. So c is called capacitive and x is called reactance. So therefore capacitive reactance. Okay, so C is called capacitance, X is called reactance, therefore it is called capacitive reactance. Okay, now we need to understand what is meant by capacitive reactance. Okay, so capacitive reactance is nothing but this is the defined as the opposition offered. Okay, so opposition offered by the capacitor, opposition offered by our capacitor to the flow of AC current, to the flow of AC current. Whenever an alternating current, you can see the diagram also if you want a clarity. When an alternating current is flowing in your capacitance, then it is going to offer a capacitance of XC ohms. Okay, so this is the resistance offered. This is the resistance offered by our capacitor to the flow of current is called capacitive reactance. Okay, so that's what the formula. I will make a simple example. XC ohms is equal to 1 by omega C. So the units of C here is farads. When you multiply with 2 pi f and make it reverse, the ultimate units you are going to get as ohms. This is called capacitive reactance. Now let us try to understand how the current and how to draw the phasor diagram and how the current is minus Gx. Generally, we'll write down this capacitance as minus Gx. So, how we are going to write down? So, actually, Xc is nothing but reactance. So, Xc reactance, I can write down it as V at an angle of 0 divided by, here you can see here, current is this, I can write down I at an angle of plus 90. Capital letter I is nothing but the RMS quantity. Capital letter I is nothing but the RMS current. Okay, so here we are going to write down V of 0 divided by I at an angle of plus 90. Okay, so this V by I is nothing but XC ohms, and this plus 90 will come to the numerator, it will act as minus 90. Therefore, the method of writing the capacitive reactance is minus J XC ohms. This is the standard form of writing an capacitive reactance. Therefore, the total impedance, okay, where Zc is called capacitive impedance. So, how to write down capacitive impedance is this can be written as R minus J XC ohms. The units of XC ohms, the units of R is ohms, the units of capacitive reactance is also ohm. So, this is in the form of a complex number where it is called rectangular form, where it is called rectangular form. And if you want to write down in polar form, okay, so when you want to write down in polar form, that is equal to root of r square plus xc whole square into angle phi is equal to tan inverse of imaginary part. So what is the imaginary part? Xc divided by R is the imaginary part. That's how to write down the capacitive reactance in rectangular form as well as polar form. These two forms are under complex number. Okay, so now let's try to, so remember capacitance, you have to write down it as minus Gxc. This is rectangular way of representation, this is polar way of representation. Now let's try to draw the two ways of representing our vectors, where this is called phasor diagrams. Okay, so these phasor diagrams we can draw it by two methods. Okay, so first method is V equal to Vm sine omega t, okay, and I is equal to I m sine omega t plus pi by 2. Okay, so this is the method of writing the voltage and current. Okay, so here you can see in the previous I had already written. So I is equal to I maximum sine omega t plus pi by 2. Okay, so now let's try to draw the diagram. Okay, so let us try to draw the x-axis is theta is equal to omega t. Let's try to draw initially v of t. So when you draw the v of t, it starts with 0 and it goes to omega m and it comes to 0, and once again it maintains its magnitude here. Okay, so this is at 90 degrees, this is at 180 degrees. This has a magnitude of minus Vm magnitude. This has a magnitude of plus Vm, and this is at 270 degrees, and this is at 360 degrees. Now coming to here, we want to draw this current. How to draw this current? So let's try to draw with another color where you'll get in clarity. So here theta is how much? Plus 90, mean the direction of, I mean at t equal to 0, just observe the waveform. So the red colored one, what I am drawing, it came to 0, and from 0 it once again goes to 0, and once again comes to 230, and it continues its path like this. Okay, so this red colored one is the instantaneous current. Okay, so at t equal to 0, the behavior of our current. So at t equal to 0, so t equal to 0 means at theta equal to 0, the I has positive magnitude. Okay, it maintains a positive magnitude. Since it is making positive magnitude, therefore the angle is also positive here. Therefore this is what the diagram. Okay, so when voltage and current are in phase, then you'll have a resistor. Okay, so now what is the angle here between the voltage is 0 and current is plus 90? What is starting first? Current is starting first. I can say that current leads, voltage lags by 90 degrees. So what is the first one? Current is the first one. What is the reference one? Second one. So what is coming first? Current is coming first. So I can say that current lags voltage by 90 degrees. So now when you see this diagram also, here you can see here how to write down. So I at an angle of plus 90. Okay, so let's try to draw the diagram. Okay, so we have V is equal to V m by root 2 at an angle of 0, and I, from I can write down I is equal to Im by root 2, maintaining an angle of plus 90 degrees. Okay, so when you see this diagram, you will get a clarity of how to draw. Okay, so now let us try to take a reference which is nothing but V m by root 2 is the RMS quantity making an angle of 0, and this we are going to treat it as an reference. And here you are going to get I is equal to Im by root 2 making an angle of 90 degrees. So this will be our RMS current. So this is RMS current traveling in 90 degrees and traveling in counterclockwise direction. Okay, so this is the current I, this is voltage V. So what is first? This is a reference, this is coming first, this is coming later. I can say that current leads, voltage lags by an angle of 90 degrees. In both methods, method 1 and method 2, the answer is same. Okay. This is how to understand a current leads voltage or current lags the voltage. Now coming to the concept of capacitor reactance. Okay, so already we had drawn the capacitor reactance. So here you can see here the capacitor reactance XC ohms is equal to 1 by omega. Omega means 2 pi fc. So here I want the relationship between frequency and reactance. I can get xc is inversely proportional to 1 by f. Okay, so now let us try to plot the graph. Okay, so when you try to plot the graph, on the x-axis you are going to have frequency, on the y-axis you are going to have xc. Now frequency is minimum. Whenever the frequency is minimum at this point, xc is maximum, so this will start at this point. Okay, and next frequency is maximum and xc is minimum, means the curve should be like this. Okay, so here we have xc is equal to 1 by f. Here we have high frequency, therefore xc is lower. Okay, at this point xc is equal to 1 by f. We have lower frequency, therefore we have higher capacitance at this point. Okay, so this type of characteristics are exhibited by our capacitor. These type of characteristics are called hyperbolic or inverse characteristics exhibited by our capacitive reactance. Okay, this is how to draw the waveform. In the next part B, we'll try to see the behavior of an capacitor. Okay, so this is the behavior of a capacitor under transient state as well as under steady state. Okay, so let's try to see the one more concept, the behavior of an capacitor under steady state condition. Okay, so now whenever we give an DC supply to our capacitor, what happens? Okay, so we have the formula, current I is equal to C dV by dt. Okay, so when you take this formula also we can get, or let's try to take the basic formula in I is equal to V by xc. So this can be written as V by xc can be written as 1 by omega c. This can be written as V into omega c. This can be written as V into 2 pi f c. So when you are giving a DC supply, what happens to the DC supply when you give? Frequency is 0. In an DC supply there is no frequency. Automatically V into 2 pi into f into 0. Therefore we are going to get I is equal to 0. At I equal to 0 means the capacitor will try to act like an open circuit. So capacitor try to act like an open circuit under the case of steady state behavior of an inductor. Okay, so in the steady state capacitor try to act like an open circuit. Why it is open circuit is, previously it was shorted. In transient state it is short circuited and it is allowing the current to flow through the capacitor. Whenever the current is flowing through the capacitor, it has charged. So the time taken to charge by the capacitor is called transient state. After getting charged, so it has 10 volts is applied and it was running in transient. The voltage across the capacitor is also 10 volts now. So as soon as the voltage reaches, automatically what happens is this will try to act like an open circuit. Now this itself will act as an source of an energy storage device. Okay, so that is what the behavior of an capacitor with AC supply as well as DC supply. Very simple. In the DC supply, under transient state it will try to act like an short circuit and it gets charged. And whenever the same charge source voltage is equal to the voltage across the capacitor, it will complete voltage is there, therefore the voltage is same, the current does not flow, therefore automatically in steady state it acts like an open circuit and in transient state it acts like an short circuit. This is the behavior of a capacitor with the DC supply. So just it charges, so no need to worry what happens to an inductor or capacitor, just they gets charged, that's all. That's what's happening in an DC supply to an inductor or capacitor. Okay, hope you are able to understand. If you feel my explanation is good, please like the video, share the video with your friends, and if you have any doubts, let me know in the comment section. And if you are watching my channel for the first time, subscribe to my channel with the name kvthulasi. So this is a free channel for the development of students and faculty. So kindly encourage these sort of free channels. Thank you for watching.